Well, thank you, Roland, for the kind introduction, and thank you all for having me here. It's a pleasure to be here with you, and I'm certainly expecting good questions and heated follow-up discussions. This is basically the work is basically going to span about 10, 12 years, starting with my master's thesis and then through PhD, and then one commercial project that we did, which went back a full loop back to my master's thesis area. So I'm going to sit down and go through the slides while I can point at things. But before further ado, I have this advances. Let's see if there's some.
Is it one you know to use now?
Maybe this.
It worked just a second ago.
Yeah. Oh, there it is. I need to acknowledge, a lot of very important and special people, including but not, limited to my master's thesis advisor, good friend, lifetime mentor, Aykut Barka. Unfortunately, he passed away, but his memory and guidance lives with me. And James is my PhD advisor, and a whole bunch of other very nice folks that I work with either technically or locals. They all helped a lot. So none of this would have been possible without them. Basically, today I'd like to take you on a road trip in Turkey on the North Anatolian Fault, starting in the east and moving along the North Anatolian Fault to the west. We'll be visiting a paleoseismic site on the eastern section, a couple of celebrate sites on the central section, and then an interesting site on the western section of the North Anatolian Fault. But basically, in a very simplified sense, the formation in Turkey and in this region is driven by the northward movement of the Arabian Plate. Here's the Bitlis-Zagros fold and thrust belt, the East Anatolian Fault, the North Anatolian Fault, and the Hellenic subduction. And the rollback of the Hellenic subduction drives a fast extension in the Aegean region that basically allows the Anatolian block to rotate along the North Anatolian Fault counterclockwise. GPS vectors clearly show that the majority of the deformation is taken up along the North Anatolian Fault. There are some residuals to the north in the Eurasian plate, but not a lot. Basically, we'll be talking about that. And the focal mechanisms also clearly show the types of deformations in this region. Basically, some truss folding in this region, and then Strexel faulting along the North Anatolian Fault, extensional normal faults in the Aegean region, and the subduction-related earthquakes along the Hellenic subduction. The interesting thing is the North Anatolian Fault, the entirety of it, almost the entirety of it, failed with large magnitude 7+ earthquakes during the 20th century. And as Rothstein modeled this with Aykut back in 1996, this is a domino-style rupture progression starting from the east in 1939. This section ruptured, and then 1942, 43, 44, 57, 67, and then 1999 August and these earthquakes. Basically, this entire section failed within 100 years. And there's this 1912 earthquake on this section. So basically, Marmara Sea is a seismic gap right now. And 20 million people live in Istanbul as a point of perspective. And probably 40 to 50% of Turkey's economy is in this region, right around the seismic gap. So that's one motivation to study these earthquakes and the North Anatolian Fault and understand why they happen, these earthquakes, where they happen, how often, and how large. And then, of course, the scientific curiosity, how these faults work in time and space. And this is a mole track from the 1999 rupture. Maybe there's a lag.
Yeah, big pictures. What's that stuff?
Oh, there it is. Okay. So these photos are from the 1999 earthquake surface rupture examples. This railroad is offset about 4.5 meters. It's, as you can see, it's pure strike slip, right lateral, dextral. And the North Anatolian Fault is, dominantly right lateral strike slip fault, but there are other complexities along the fault where it makes a releasing or a restraining band. For example, in this area where it makes a right step, a releasing band, it created this almost 2-meter high normal fault scar. And this is pretty close to the maximum displacement for the 1999 Izmit earthquake. It's at 7.4. So the general understanding for the North Anatolian fault, and in terms of its hazard applications, is that it ruptures every 200 to 300 years, magnitude 7.1 to 7.4 earthquakes, with a maximum displacement of 4.5, 5 meters. And is that the case? That's what I'm trying to dive into a little bit here, because it has big implications when it comes to safety and designing for critical infrastructure and how the faults work as well. So as I said, we'll start off with this location on the eastern section where the 1939 earthquake happened. It was a 7.9 earthquake, pretty much the largest strike slip earthquake in Turkey on the North Anatolian fault, at least recorded. And then we'll move on to the central section and then to the western section. So this site is really interesting because Ross Hartleb, another James Dolan student, he did most of his trenching, and I helped him a lot in this Çukurçemen site. And I did a lot of trenching in this Yaylabeli site. And the interesting thing is a lot of village names are very geomorphic in Turkey. Çukurçemen literally means grassy depression. It's a set font, pull apart. And Yaylabeli literally means cycle bench. Can't get more specific than that. So I'm going to focus more on the Yaylabeli site, the site that I worked on, and these sites are, in this kind of areas. Here's an overview of the site. It was a very beautiful village with this grassy depression, with a very small fan dumping fine-grained sand and clay into the marsh on a continuous basis. And it's a beautiful site for trenching because there's continuous sedimentation, there's continuous organic material growth and burial, and it's very small. So here's a photo of the site after I put in 2 trenches. We excavated to a total of 4 trenches in this area. Basically, the fault comes into the marsh and then it makes a small releasing step over into this location and then continues outside the area. This is a general view of the one of the larger trenches that I put in. This is benched and it's about 4.5 meters deep. The dark black or dark brown layers are all peat horizons, and then in between we have real nice clay and sand materials. And here's a small fan that's providing the sediment on a continuous basis every year when the snow melts on these ridges. So here's the fault zone from that trench. Here the fault is opened up a little bit because it's starting to step over. It provides a really good opportunity to tease out events in the event stratigraphy. Again, these dark horizons, the browns and the blacks, they're all organic rich peat horizons. We sampled and dated all of them. And also we found a lot of charcoal material. We've dated them as well. And then in between we have this really fine clay and sand material. Move back. In this exposure and in this site, we basically found and identified 5 earthquakes in the last 2,000 years. 3 of the interseismic periods are about 200 to 350 years long. With one exception, the earthquake, the interseismic period that precedes the 1939 earthquake is 685 years, almost 2 to 3 times longer. And the 1939 was a real large magnitude earthquake with a lot of displacement.
Do you get slip estimates of the older earthquakes?
Yeah. Probably next slide or after that. This is another trench because when you bench your trenches, there's always the question, well, am I missing an event at the bench? So after drying the site a little bit, we put in this slot trench, and this is the fault before it steps over. So it's very concentrated, and basically 70 to 80% of the entire deformation that's on the North Anatolian fault is right here. You can put your finger on it. It's very concentrated. And here are the trench logs. So this is that trench log T4, the slot trench, from east to west. As we go down on these logs, it goes to west. As you can see, the fault zone is very concentrated, and then it starts to open up as it steps over. It's wider with multiple strands, and then it steps over to the other side. And again, the black and the brown colors are the peats. This is a simplified version of my logs because in this kind of scale, it's hard to show everything. And then whites are clays, and then blues are sand layers. And this is the type of high-resolution stratigraphy that we teased out of those five earthquakes from. So here's a plot of the dates. Basically, these are not all the dates, but the dates that constrain the timing of the events. The vertical scale is the depth below ground surface, and the horizontal is time. And when we plot a curve, the sediment accumulation curve through these age dates and their depths, the sedimentation is pretty much continuous. There's no hiatus in this record. So that's a good thing for paleoseismology. And now when we plot the earthquakes that were identified according to depths, they also work out really well. These age ranges are based on the peat dates. And then these ages are the historical earthquakes in the historical records. So we have all these earthquakes recorded in the historical data, except for this one. And that's a chaotic period in Anatolia. But basically all the others are recorded in detail. And they all match really well. So again, we have 5 earthquakes, but then the long interseismic period, that's about 700 years preceding the 1939 earthquake, is 700 years, almost 2-3 times longer. And the question is this an exception, or is this does this happen all the time? And what does it mean? Because this earthquake had a real large magnitude. It was 7.9, maybe 8. And this is just to reiterate that point I just made. So I could measure an offset road for his 96 paper. And it was about 7 meters offset for the 1939 earthquake. But then when I talked to him after the 99 earthquake, he said, well, those displacement measurements may be minimum because he was measuring right at the fault. He was not really accounting for the far field deformation. It's not that far, but still no far field deformation at all. When we resurveyed this area with Ross, we actually estimated 10-meter displacement on this road. And that makes sense because you have 2 to 3 times more interseismic period, a much larger earthquake, and you get almost twice as much coseismic displacement.
So to get to 10 meters, you counted that bending of the wall?
Yeah, counting the bending of the road, yes. So let's move on to the central section. This is the 1943 rupture. It was a 7.2 earthquake. And I'm going to talk about 3 sites here, 2 sites in Eksik. These are slip rate sites, and 1 site in Tahtaköprü. So this is the site in Eksik. It's an interesting location because Aliç is a paleoseismic site by Sugai et al. From '97. So we have the opportunity to correlate our slip rate and displacement, cumulative displacement, with their paleoseismic record. And this is the paleoseismic site. The slip rate site. We mapped in detail offset alluvial terraces. Here's the North Anatolian fault, and the drainage is captured here. And we not only mapped the terrace extent in detail on the surface, but also we hand dug trench pits, test pits, or small trenches, and basically identified and found the tips of these terrace deposits to really tighten our displacement measurements. And when we did that, we actually found charcoal material both above and below these terrace deposits. So that gives us a really good constraint on the terrace ages. But we also sampled chlorine-36 samples, limestone cobbles on this terrace surface. And we dated those with chlorine-36 cosmogenic nuclide dating. And the reconstruction of the offset gives us about 46 meters. That's the preferred displacement. But I'm pretty generous and conservative when it comes to uncertainties. We give plus or minus 10 meters of uncertainty with everything considered. So this plot, the blue lines show the probability distribution functions for the cosmogenic nuclide ages. And these ages, the colored ones, show the charcoal age ranges from beneath the terrace deposits, and this one from above the terrace deposits. So this is a really good interval to constrain the age of the terrace deposits. And that's about 2100 to 2400 years. And when we combine both the displacement and the age, we get about 20.5 millimeters slip rate per year for the North Anatolian fault. So the geodetic slip rate is about 25 millimeters a year. There's a bit of a discrepancy. And when we use the radiocarbon dates alone, the age range is a little bit more, the uncertainty is a little bit larger, but basically the preferred slip rate is still the same, 20 millimeters a year. So two different age constraints, which is a good thing because that gives us higher confidence in our slip rate estimates. So let's move a little bit to the east, to Tahtakköprü site, still on the 43 rupture. Here we have a offset drainage in an alluvial fan, and we mapped the offset here, and it's about 57 meters. And we sampled the surface, the alluvial fan surface. This time we used quartz gravels and cobbles, and we use barium 10 dating. I'm going to skip some of the details, and I'm happy to answer them after the talk, but basically we use the oldest age as a representative age for the surface because of thousands of years of agricultural tilling of the surface. Basically, you're losing the fines and then you're concentrating gravels, coarser material from the, basically you're exhuming them to the surface. And when you combine both, about 3,000 years and 57 meters, you get 19 millimeters a year of slip rate per year. So it's pretty consistent with the other side. When we put these two side by side, similar catchment areas, the fault is pretty well expressed in a narrow zone in this area. We have three different dating methods: chlorine-36, radiocarbon, barium 10, different displacement amounts, 46 meters and 57.5 meters. But we have pretty much indistinguishable slip rates, about 20 millimeters a year, very consistent. So what does it mean in terms of displacement per event? The 1943 rupture, again, according to ICUT's measurement, was about 4.5 meters, and that's pretty much the maximum displacement for this rupture. But when we combine the Sugai's paleoseismic site, they have 5 events in their trenches for the last 2,000 years, very similar to the eastern section trenches that I showed you earlier. And when we combine them with our 46 meters of displacement, basically, if you think 4 or 5 events in 2,000 years, that's almost 9 meters per event. That's probably too high. But in 2,200 years, which is more representative for the surface state, and if we say we have 6 earthquakes in that kind of time interval, this time we have 7.5 meters per event. So that's, again, at least 50% higher than the 1999 Izmit and Düzce earthquake type displacements. So it's the 5 meter is not necessarily characteristic, it's looking like. One other thing that comes to mind, go ahead.
Are you confident that it's like fully coupled?
Well, basically the displacement we are measuring is at the surface. So yes, we are thinking that it's fully coupled, and there may be other deformation outside these near field fault locations. But we choose these sites because they are really, the fault is really well expressed. So the so-called off-fault deformation is probably not significant at all in these kind of locations. Yeah.
How do you estimate like the magnitude of the events? Like the previous one?
The previous one, the 1939 was 7.9. Because
but the earlier event,
the earlier made like the sleep, so
we have not. No. For that, we will need to know the total rupture length.
Right.
And we can do that because we have more paleoseismic information. We can do that. I'll show you. That's one of my last slides. But I haven't calculated that for the previous events. But basically, any record that you see in the paleoseismic trenches, that means it's a large magnitude earthquake that ruptured to the surface. So it's very highly likely that they are 6.8 and larger. And one question that you may ask is, well, what if your paleoseismic record is not complete? What if you are missing earthquakes in your trenches like Sugai? How are we sure if they had actually had 5 events? In Erzincan, in the eastern section, yeah, we had close to 10 trenches in 2 sites, so we have a really tight constraint that we don't have any more earthquakes in those. But in here, there's another method that we can test. This is the trench site, paleoseismic site from Sugai. This is the displacement site that I showed you from the calorimeter 6. And this stretch of the North Anatolian fault is not good for paleoseismic trenching, but it's good for dendroseismology because it's a nice forested section of the fault. The fault morphology is beautiful. You can still see, the rupture mold track from the 1943 rupture. It's expressed as beautiful back-facing scarps and mold tracks and depressions and linear depressions. And one thing that stood out when I was walking along the stretch, Pinus sylvestris, or as the locals call it, yellow pines in this region, are these beautiful, very straight pine trees. They are as straight as a number 2 pencil. But when you look at the fault zone, they are traumatized in every which way. They are tilted, they are bent, they are broken. They have these candelabra growths, which basically that's the crown snaps with the strong ground motion, and the new growth is candelabra. So I thought, well, maybe I could tease out some more event stratigraphy within these tree rings. And whoops, skip too much. So yeah, I bought a Swedish increment borer, and I cored a whole bunch of trees, both parallel and perpendicular to the fault orientation. This is one of the examples. This is another, it's an invasive method, but it doesn't harm the tree. And in the early days, they used to plug the holes so that nothing would get in, but then they realized if they accidentally put a bug in, it's stuck there. So we leave the holes open so the sap actually flushes everything out. It doesn't affect the tree. And here's an example of the measurements. So let me walk you through this a little bit. The blue shades are the cores, both perpendicular and parallel to the fault. These are uncorrected or unstandardized ring width measurements. And the red is the standard that I have developed for the population that I sampled for this area. And what does the standardization do? It basically, the trees, when they are young, they grow real fast. And then when they reach maturity, they grow at a more constant pace. Basically, to standardize it, dendrochronologists developed this method, and you can standardize that. And this is basically for the entire population that I sampled, not just for this tree.
Does the standardizing take seasonal signals as well, like droughts or?
It doesn't take those out, which is a good thing because the dendrochronologists originally used these methods to look at climate information. We actually looked at regional climate standards, which includes hundreds of trees, to see if the earthquake signal that I'm seeing also exists in those that are away from the fault. Even if they are on the fault, they use hundreds of trees. So 1 or 2 earthquake-related trees would have been drowned in that kind of signal. And we don't see this signal in the regional climate dendrochronologic records. So right in 1943, you see this immediate sudden growth suppression. And this is one of my favorite trees in that region, and I'll show you why. So this is the entire core that I sampled out of the tree, and it goes way back to 1693. Okay, this is the uncorrected or unstandardized ring width measurement, the original measurement. And this upper blow-up section is from the tip of it, and in this area. Basically, when you look at the rings, the blacks and whites are individual seasons. And you see, until 1943, the tree is happily growing on a steady, constant pace. And right at 1943, boom, it has a growth suppression for about a decade or 2, and then it gradually recovers after that. And then, reaches its previous state again. So this is a textbook kind of example of dendroseismology that I basically first read on Gordon Jacobi's papers. He was an amazing pioneer in that. So this basically shows all the trees. The lower graph shows my confidence level. Basically, I took 22 cores from 14 trees. Okay, and as you see, as you go back in time, the number of trees and cores are less because not all the trees are as old. So that's transparency in my confidence level. But when we look at the signal, basically all the color plots in the back are from individual cores, and the red is the standard. So going back in time, I don't see a trauma as significant and distinct as the one we see in 1943. So here's another point of confidence on Sugai's paleoseismic site, and I can say, well, okay, at least for the last couple hundred years before 1943, I'm not seeing another obvious event. So another point of confidence in that record.
So you could have done what Danny suggested, removed kind of a common mode climate signal by taking trees away from the fault zone, and maybe that would see smaller features. That
I have a slide on that. I have the regional one. I did not take. I did not want to take out the climate signals as well. Then it would be, I think, modifying and pushing the data too much. I want to leave it as objective as possible, so that we see both the climate, but we take out the youngling growth out. But then, even in this somewhat noisy data that shows the climate signals, 1943 still stands out. And I have a side-by-side this standard versus the regional climate standards. They don't have this signal. I can show it at the end of the talk.
Can I ask one question?
Yeah.
What is there any empirical relation? How much growth is going down versus magnitude, or what the size is depending on the structure?
So I don't think there's a one-to-one relation between the earthquake magnitude and the signal that we see on the tree's growth suppression.
Okay.
Basically, anything that traumatizes the tree, and that could be rupture of the tree's roots, toppling of the crown, or immediate down-dropping of the groundwater level, or increasing of the groundwater level, or death of the neighboring tree. All these things that affect the health of the tree, but they are sudden because it's a result of the rupture.
But there's no physical threshold.
That would be hard.
I know.
Okay.
That would be great.
I just curious. Okay.
Yeah. No, that's a good question. I wish there was one. And I should say, I like to adopt different methods to reduce the uncertainties, but I'm not an expert on all these methods. For example, I sampled, processed, and dated my chlorine-36 or beryllium-10 cosmogenic nuclide samples, but there are other experts on that who's pushing the envelope. How can we tighten the uncertainties and make more out of these kind of methods? So Bob Pinkel, actually, I think he still has an office. He was my mentor at Lawrence Livermore Lab, so I did my time with him at the lab.
So all your dating you did?
Yes, dating my samples there.
Yeah.
And Michaela Kashkarian, she showed me how to do the radiocarbon sample treatments. So let's move on to the western section of the North Anatolian Fault. And this is an interesting site for many different reasons. But before I dive into the site, let me say that the North Anatolian Fault actually splits into various strands in this region, in the Marmara region. And we are looking at the northern strand, and the northern strand is the fastest among these three based on geodetic measurements. But it's not the full 25 millimeters a year on every single strand, obviously. So I'll be focusing on this site. This was initially my master's thesis area, but then between 2000 and 2002, and then when I started working as a consultant, we learned that they were going to build a bridge across this peninsula. And we went there with a lot more resources, and we did a lot more research in there. So I'm going to show you both information. Basically, this location is where the 1999 surface rupture dies. Here in Gölcük, where I showed you the 2-meter high normal fault scarp, that's where this fault makes this releasing band. And in here, there's the 5-meter, the maximum coseismic displacement. And through all these small releasing steps in the Gulf and by the time you reach the Hersek Peninsula, there's no displacement at the surface, zero. So initially, back in 2000, 2002, we put in 17 trenches totaling about 1.2 kilometers and some geophysical methods to find where the fault is on the peninsula because we didn't see any rupture. But the geomorphology of the peninsula is basically composed of a fan delta, an uplifted ridge that's 28 meters above sea level, and uplifted marine terraces nestled on either side of this ridge. This is basically Pleistocene deposits, and there's a lagoon here. Okay, so here's a close-up, and I'll move into this location next. This is one of the earlier trenches, early 2000 trenches. These are all the trenches, and I'm going to show you this one. The only deformation at the surface that we saw was this crack, this tiny crack with no apparent offset on it. But then we put a trench across it, and it's, the fault is here, it's black and white, literally. On one side, you have uplifted Pleistocene deposits, and on the other side, you have this, back tilted and uplifted marine terrace deposits. But there's no 99 rupture on it. So I try to, as a master's student, I try to address, why, this fault stopped here, because the geometry wasn't as clear back then. And I tried, multiple fault geometry methods with using elastic modeling in half space. And this restraining step over, the left step over with an angle here, was the best fitting model that showed that matched the geomorphology. Basically, this is the asymmetric dedular heel that's about that's 28 meters above the sea level. And here's the depression of the Hersek Lagoon. Okay, this basically shows that transaction pretty good. This is the cross-section location. And this is an offshore seismic profile here east of the peninsula. And you see the folding and the depression on this seismic profile. And that shows this, it matches pretty well. And in Coulomb modeling, a basic modeling, this geometry puts the unruptured portion of the section in the stress shadow area. So I thought, well, that's a pretty good explanation. That will be my master's thesis. But then, for the bridge crossing, the risk is much higher, and they wanted to build the world's second longest suspension bridge across the North Anatolian fault zone right here. So I was working at Fugro back then, so we brought in deep sea vessels for drilling, shallow jackup platforms for drilling, and CPT geophysics vessels for deep sea and near coast, and CPT trucks and various geophysical, and we did a lot more trenching as well. So we did a lot more trenching. We actually did put in 16 more trenches, totaling 1.5 kilometers, reaching about 1.7 to 4 meters deep. And we did not see any surface faulting. We dated different horizons. The unfaulted horizons that we were able to data across all these trenches was about 170 to 300 years old. So the last at least 170 years, probably 300 years, there's no surface structure across this peninsula. So what's going on here? Basically, here's the really detailed bathymetry that we acquired and processed and meshed with the onshore topography. And I'm going to show you a couple cross-sections, geophysical cross-sections from the east of the Hersek Peninsula and then west of the Hersek Peninsula. But basically, when the fault reaches Hersek Peninsula, this dedular heel, it looks like it refracts around that. So it makes me believe that this is a persistent, some sort of an asperity in this location. And
so there was there were 2 earthquakes in 1766. Can you rule out those?
It's very unlikely based on our exposure dates.
Yeah.
But I do allow that in my model. I'll show you that, yeah. And then the fault basically splits into a northern strand and a southern strand west of the peninsula. So here are the profiles east of the peninsula. Basically, the reddish profiles are deeper, tens of meters deep, and then the gray ones are high resolution subbottom profiles, the upper few meters. As you can see, the fault traces reach pretty much all the way to the surface, the sea floor. except for the closest one. In here, you see that the fault actually does not reach the surface. There's an unbroken reflector here closest to the Hersek Peninsula. When we go to the west of the peninsula, now you see that the fault zone is opened up, split into two, and most of the traces actually do not reach the surface. So the fault rupture actually dies at or just east of the peninsula and does not really reach the surface anymore west of the Hersek Peninsula. There are some arguments out there that they saw some cracks in the seafloor. They dove down with a submersible. My classmate from masters, she did, and they say but the displacement on that is less than 0.5 meter. So the majority of the slip that we saw 5 meters of coseismic displacement doesn't make it across the Hersek Peninsula. Some slip leakage can happen. It happens in large magnitude earthquakes, but and then there's some creep story there as well. I'm not going to go into that much. So on the left here, we have all these trenches, and then yellows are the blacks are trench locations. The yellows are test pits where we couldn't put in a continuous trench. And these blue dots, that's the interesting story here. I'm going to talk about that more. Basically, these dots are surveyed locations for a 6th century Roman aqueduct that crosses the North Anatolian fault. This E is another location that we surveyed it. E is a cistern, Roman cistern. F is a Roman bath, and then G is a Ottoman era mosque. So let's move on to that. Now the archeoseismology part. So this site is really interesting because it's called Helenopolis because Helen was the name of Constantine's mother, the founder of Constantinopolis. So it's been always important, and Justinian actually built a lot of structures here, which I'm going to talk about. And this has been an important route because this dashed line is a route off of the spice route, that goes all the way to Middle East, Baghdad. Actually, I grew up on this road, and it was called Baghdad Boulevard. I never thought why it was called Baghdad Boulevard, but when I worked on this project, it's actually the route to Baghdad, basically, between Europe and Middle East. And they either had to go around this entire Gulf, or sometimes they crossed the bay where it was the closest, which is the Hersek Peninsula or Helenopolis. And actually, one of the first waves of the first crusade ended in this Dragon River. There was a fight in that valley, and that was just finalized there. But let's move on. That's history. So here's the aqueduct, the Roman aqueduct. It's a different kind of aqueduct because Romans actually normally build their aqueducts on arches. They are elevated structures. This is a weird kind of aqueduct. It's on the ground, and there are towers, but the aqueduct itself is on the ground within a wall. And north of the lagoon, this is the Hersek Lagoon that I showed you. Actually, north of the lagoon is just the tongue and bell type clay pipes. And it's actually, you can see it was damaged and it was repaired by the previous broken pieces of the pipe itself. So they put in a new pipe and then they used the old pieces to plaster around it to make it more strong, I guess. But the cool thing is, the pipe is a perfect strain gauge going across the North Anatolian fault, which we mapped. So here's us mapping it. These flags, the wrought irons, this is where we found the margins of the aqueduct during the low tide. And these were surveyed later on. This is us hand digging the pipe section onshore. And this is the cistern, and this is the Roman bath, and this is the Ottoman mosque that was built in 1508, and 2/3 of it collapsed during the 1509 earthquake. Bad luck and bad location choice. So the coolest part of the story is Justinian, he was a really active emperor, Byzantine emperor, and Procopius was his historian. He published 3 books on him, 1 volume on his wars, 1 volume on his construction projects, and an unofficial volume on the juicy stuff, which I'm not going to go in. So the volume on the construction was published in 561 AD, and it describes Hersek Peninsula's geomorphology, geomorphic setting in detail. It says the city was suffering from shortage of water and oppressed by thirst. So Justinian improvised a marvelous aqueduct that provided with unlooked for supply of water. So improvisation is interesting because, as I said, this is not a typical aqueduct for that time. So basically, Justinian ruled between 527 and 565. This book was published in 561. So we know that the aqueduct was built between 527 and 561. That's a pretty good constraint on the strain gauge. Okay, so here's the fun stuff for us earth scientists. These blue dots, as I said, is the locations where we mapped it. And it's offset right laterally 14 meters, right where the North Anatolian fault is. Okay, and because we surveyed top of the aqueduct, we also have a vertical displacement across the profile of it too. It's up to 0.7 meters. So when I combine this information, basically the time of construction, the strain accrual period is, according to the historical records, the last earthquake predating the construction of the aqueduct is 478 AD. Okay, and based on our trenching exposures, we think the last earthquake to have ruptured through here is the 1509 earthquake, which is a big earthquake, large magnitude earthquake. It's called a little disaster in this region, basically. So, and when we combine that, we get a slip rate of about 13.5 millimeters a year. That's relatively slower than the geodetic rate, but it's pretty, you know, it's up there. The next best estimate was 10 millimeters a year offshore, but I think this is a better estimate because it's much tightly constrained. And going back to your question, Roland, if we assume that, you know, that 1766 earthquake was there and we somehow missed it in our paleoseismic record, it still gives us, 13.5 millimeter a year displacement, but the uncertainty on the lower end is a little larger. It basically, instead of plus or minus 1 millimeter, now we have plus 1 millimeter minus 3.5 millimeters a year. And the vertical slip rate is about 0.6 millimeters a year we get out of this. So the interesting thing here is, if actually the 1509 earthquake is the last earthquake to rupture through this location, now our seismic gap has been sitting there for 500 years. And what we learned from the 1939 rupture, you know, the longer we wait, the bigger the earthquake magnitude and the displacement is. So the infrastructure that's going to be built across this site needs to accommodate that kind of deformation if they're serious about that. And when we look at the paleoseismic record along the North Anatolian fault, so this is the map view, and here are the individual trend sites, and the dots are the paleo earthquake locations, and the bars are the uncertainties. This yellow bar is the 20th century rupture. Well, there must be a gap in between here, but that's my bad in the graphics department, sorry. But basically, you can see that in the past, end-to-end ruptures within a really short time, like within a century, has occurred, but it's not a rule. We also have these other ruptures that does not rupture the entire section, especially in this area where I showed you the trench location. We have this about 700-year gap, and it resulted in a much larger event. So there is the reason why I named the title Bi-modal behavior of the North Anatolian fault. It's not always this 200 to 300 year recurrence interval, 4 or 5 meter coseismic displacement. Sometimes it's twice that. And the other thing is slip rates. So how do they compare? Again, the top is the map view. This green continuous line is the geodetic slip rate. And these other colored bars are geologic slip rates with different methods. They may be cosmogenic nuclide dating, climate response, or beryllium-10, or radiocarbon, or OSL. One story that pops up here is that they're consistently lower than the geodetic slip rate. Okay, and this lower graph is in time. Okay, the geodetic slip rate is only actually here, but if we just extrapolate it for comparison purposes back in time, the geologic rates that go back in time, back to about 60,000 to 70,000 years, are also pretty consistent based on, with the type of resolution we have. And that's slower than the geodetic rates.
How far back does the geodetic rate go?
It started in the 80s, 1980s, like 88, 87, I think, the first GPS geodesy. That was with Rob Radlinger from MIT, and I could park on my master's advisor. So the question is this a persistent feature, or is this a transient feature, or are we missing something? So is there really a discrepancy? I don't think there's really a major discrepancy. First of all, I mean, the geodetic rates are within spitting distance of the geologic rates. It's pretty close to the uncertainty that we have. And there are other structures out there. The places where we measured geologic slip rate is not the only place that you may have geologic slip. For example, there are these offshore structures in the Black Sea. And between the North Anatolian fault and these offshore structures, I wouldn't be surprised if there are other faults that may be accommodating a fraction of a millimeter, but there may be multiple of them, accommodating over a range of deformation zone. So I don't think there is really a discrepancy between these rates. It's just basically we measure these rates where we see them the best, right? And that might be the case. So in summary, we recognize 5 earthquakes during the last 2,000 years, pretty much no matter where you go along the North Anatolian fault. So that's consistent. There are 3 interseismic periods that range between 220 to 350 years, but there are also 500 plus, almost 700-year-long interseismic periods that result in real large magnitude earthquakes and displacements too. The geologic slip rates are ranging from 15 to 20 millimeters a year. That ranges from 1,000 years to tens of thousands of years. And the combination of slip rate story, the cumulative displacements, and the nearby paleoseismic trench sites actually give us an average coseismic displacement of 7 to 8 millimeters event. So what we see on the 1939 rupture location, the 10-meter displacement is not really out of the ordinary. And we see that on the eastern section of the North Anatolian fault, we see that on the central section of the North Anatolian fault, and we may see it on the western section when the seismic gap fills in the Marmara region. So basically my take-home message is, everybody thinks that the North Anatolian fault is a really simple, well-behaved fault. We understand it really well. That's why we are, sending guys like Oz to Turkey to trench that so we can compare it to San Andreas fault. But we may be a little bit too confident about our estimates. Like I tried to show you, and I hope I convince you that there's at least a bi-modal behavior going on with the North Anatolian fault. It may be more, I don't know, but the signal that I'm seeing, there's at least 2 different types of behaviors. So we just want to be careful, what we call, where we call it. It's because there are implications both for our, scientific curiosity and understanding how these faults operate, but also much shorter term implications for critical infrastructure. I like to leave it with that. Thank you.
Great. All right, we'll open it up for questions. Online, just raise your hand. Any questions?
Did they build a bridge?
Yes, they have.
Oh.
There it is. Yeah. So one bad news that we gave them, we found offshore landslide, and we found some secondary fault strands. So they shortened the suspension charge and the superstructure of the bridge to avoid those. They crossed the fault zones with a fill prism. It can take a lot of beating and it won't collapse. And then that made the bridge 4th longest bridge at the time that they built. They wanted to go for the 2nd longest. I think now it's down to about 7th or 9th longest suspension bridge in the world. Yeah.
Another question?
Yeah.
So like that last slide about comparing the geologic rates to the geodetic rates, like, is your takeaway, like, I'm going to take all my geological measurements and just like add a factor of 2 fudge factor or factor, well, like, can you know the next one? Yeah, that one. Like maybe not factor of 1.5.
30%.
Yeah.
Yeah. So
Is that like your takeaway, or do you think maybe there's something interesting where now the fault is slipping faster for some reason? Like,
so if you asked me that question before I showed you this,
Yeah.
I would say that approach is done by the engineers, civil engineers. So you give them, as an earth scientist, your best estimate, and then based on the criticality of the structure, they add a certain amount of factor of safety. It goes on their end. But now that we know this, we told this to the bridge construction company, so they basically built their structure and located their structure accordingly. Plus, basically, based on what we told them, they also added their still factor of safety just for the engineering purposes. But we wouldn't do that blindly on both ends. So back to your question, if I didn't have this information, and if they asked me, I would give them my best estimates based on what I know, and then they would add their engineering factor of safety on top of that.
How much does expense go into the equation? I mean, they have to build for safety, but they also have, that costs more money.
Totally. Yeah.
So they're kind of, you think they just split the difference?
For that project, they can't. They can't afford to split the difference because if the bridge fails, all of their investment is gone, right? And I'm not considering the legal and other ramifications of it.
I mean, that seismic gap to the west is that domino is going to fall at some point, right?
Yes.
If it's in the next 10 years or 50 or 100 years, it will.
Yes.
Yeah.
Exactly for that reason, they wanted to avoid any fault crossing with their superstructures. That's why they put an approach ramp that's a fill prism, basically, that's on any of the faults that we mapped in great detail. And then outside that, their engineering basically takes into consideration of the strong ground motion. We did also a PSHA model for strong ground motion and the seismic loads. As a geologist, I provide the inputs for the fault line sources in that PSHA, and they also looked at the seismicity and they looked at the aerial sources, and they did their analysis based on that too. But I can tell you, as far as I know, by the time I was detached from the project, they were basically taking the conservative approach because they knew with all this information that this was a high-risk site. Yeah, they spent about $17 million over a 6-month period for all that information. So they use that.
So overall, would you say the slip earthquake behavior here sort of follows a slip predictable model or time predictable? I mean, that's why I was asking about previous slip, right? Did the last earthquake also have a lot of slip, and therefore it took 600, 700 years? And the next one in the east, we shouldn't expect for quite a while, or is it?
So that will be the slip predictable model.
Yeah, exactly.
Right? I think what we see here is time predictable. Basically, the longer
you wait, the bigger
the larger the earthquake. But then I think it resets after that, and I don't know why. It either goes off every 300 years or 700 years. There must be. There are ideas about the interplay between the North Anatolian fault and the East Anatolian fault. I have some animations, basically plotting all the historical earthquakes in the region to see if one goes on, the other one's silent. And yes, there is some truth to that, but I think the jury's still out on that.
So then, if the Marmara Gap fails now, how big will it be? Given that there are 20 million people in. Yeah,
when we look at the extent of the length of the seismic gap, if we use that kind of a formula, it's somewhere between 7.2 and 7.5. And the question is it going to rupture in one go, that entire seismic gap, or as you can see here, there's a step, or is that going to be like another barrier for the next earthquake? So basically, if everything ruptures in that region using the standard formula, you get like magnitude 7.5. If you divide it into 2, you get 7.2.
All right, last call for questions. Then let's thank Oz again, and we'll have refreshments on the balcony. Thanks very much.
Great talk, Oz. Thanks very much.
Oh, thank you.
I really like how you incorporated lots of data and history